This is notes 3.2, which are on exploring quotients of polynomial functions. And question number 1 asks us to use does most to explore the graphs shown below. And we have to know any holes or any asymptotes. So our first function that we have here is a quotient of two polynomial functions. So how do I know it's a quotient? Because it's division. And how do I know there are two polynomial functions? Because we've got a quadratic on top and a linear on the bottom. So we've got a quotient of two polynomial functions. So I want to explore and see, well, what's going to happen if I have a quotient of polynomial functions? So before we actually use does most to explore this, we would expect to have a restriction when x equals 1. X cannot equal 1 because when I divide by 1, it doesn't work. So I would expect to have a vertical asymptote when x is equal to 1. I want to explore the graph and see what's going to happen if I do this. By the way, you're going to need some scrap paper on the side to do some algebra, or you can do some of the algebra on the back, okay? By the way, I'd like you to have Desmos open so you can kind of explore this as we are going through this. So if you need to flip back and forth between the video and Desmos, that's fine. So when I graph out f of x is equal to x squared minus 1 over x minus 1, I end up not getting an asymptote when x is 1, which is really strange. I would have expected that I would have gotten an asymptote when x equals 1, because it's undefined when x is 1. So why didn't this happen? So let's go ahead and do a little bit of algebra and see what ends up happening. So if f of x is equal to x squared minus 1 over x minus 1, I can factor that numerator. It's a difference of perfect squares. So I've got x minus 1 times x plus 1 over x minus 1. So then when I factor those, when I cancel those two out, I end up getting x plus 1, which means that my graph is going to behave like x plus 1 for the most part, which is why when I look at my graph, I have a linear function that has a slope of 1 as well as a y-intercept of 1, okay? So it's behaving like x plus 1. However, remember, we talked about looking at the fact that x equals 1 doesn't work. So if I were to look right here, if I were to do f of 1, I still get an undefined value. And if I were to kind of explore the values that I have here, sorry about that, right here, when I get to 1, it's undefined, but when I get really close to 1, I have values. But everything around 1 will work, but once I get to 1, it's a no-go. It doesn't work anymore, okay? Therefore, I can conclude that there is no vertical asymptote, okay? And that I have a hole at x equals 1. What does a hole mean? It means that if I were to graph this out, it would work until I get to 1. It would be an open circle, and then it would keep going. It works everywhere except for 1, okay? So now let's look and see, do I have any horizontal asymptotes? So if I were to look at this right here, since this is a straight line, I don't have any horizontal asymptotes. I don't have any y values that it's approaching with my end behavior right here. So I can conclude that there is no horizontal asymptote, and that the slant asymptote, it ends up being a slant line anyway, so we don't have to worry about that, okay? So now let's take a look at the next example. F of x is equal to 3 over x plus 1. We know that we have a restriction at x equals -1. However, this time I don't really have anything that's going to cancel out. So I would expect to see a vertical asymptote when x is -1. Let's go ahead and graph this one out and see what ends up happening. So I'm going to say f of x equals 3 over x plus 1. Let's see what we end up getting. If I were to zoom out a little bit, let's see if this would maybe look like I could possibly have a vertical asymptote at x equals -1. So I'm going to graph out x equals -1 and see what it looks like. And it definitely appears to have a vertical asymptote at x equals -1. So I can say that this graph has a vertical asymptote at x equals -1. Does it have a horizontal asymptote? Absolutely, because it looks like it's approaching the x-axis on both sides. So it looks like it's approaching y equals 0. So I'm going to say y equals 0 right here. And I can see, oh, yep, definitely it's approaching y equals 0. So it has a horizontal asymptote at y equals 0. It doesn't have a slant asymptote because it's not approaching a certain point on a slant line. So my graph here does not have a slant asymptote. And there are no holes because where we could possibly have a hole at x equals -1, we actually have an entire asymptote, so there's no way that we can have a hole there. So we'll say that there is no hole right here. Okay, so now let's take a look at the next example that we have here. And I actually want to do a little bit of algebra with it before I move on. So this time we have f of x is equal to x plus 1 over x squared minus 2x minus 3. And what I'm going to do is I'm going to factor that denominator and see what ends up happening. So I get x plus 1 over x minus 3 times x plus 1. Well, let's take a look at this right here. This x plus 1 and this x plus 1 will cancel, and I have an x minus 3 left over in my denominator. So I know that it's going to behave like 1 over x minus 3. Okay, and we'll verify that with decimals in a minute. But we also know that we have restrictions when x is equal to 3 and x equals -1. But these are going to end up being two different kinds of constrictions. This one right here, once I simplify it, this x minus 3 stays there. So that means that I'm going to have an asymptote at x minus 3. But at x equals -1 right here, I'm going to have a hole because these two will cancel each other out and it will behave like this. And this graph does not have an asymptote at x equals -1. Therefore, this graph will not have an asymptote at x equals -1. Okay, so let's go ahead and verify with our graph that we have on Desmos. So if I were to look at this right here, I would end up getting, let's go ahead and type it in first. So f of x equals x plus 1 over x squared minus 2x minus 3. So let's delete this out of here for right now, as well as our asymptote equation right here as well. So if you look right here, it's clear that we only have one asymptote, and it appears that the asymptote will only happen at x equals 3. So let's see if we have an asymptote at x equals 3. It appears like we do. Now, if I were to look and see, well, do I have an asymptote at x equals -1? Let's go ahead and do that. There is no asymptote at x equals -1. However, if I were to follow my graph right here and go to -1, it would try really hard to get close to -1, but then at -1 it's undefined, which means that I have a hole at x equals -1. And let's just verify here as well, f of -1 is still going to be undefined. Okay, so then I can conclude that I have a vertical asymptote at x equals -3, sorry, at x equals 3, not -3, and that I have a hole at x equals -1. Okay, now remember how I told you guys that it behaves like 1 over x minus 3? So let's go ahead and see if it really does behave like 1 over x minus 3. So let's do f of x is equal to 1 over x minus 3. It's exactly the same. The black right here will line up with the red that we had originally before. Okay, so they do behave exactly alike. So now the last question is, do I have a horizontal asymptote? Well, it appears to approach the y-axis on both sides right here, so definitely have a horizontal asymptote, y equals 0. Okay, so right here, I can say that I have a horizontal asymptote at y equals 0, but I don't have a slant asymptote because it's not approaching a slanted line. Okay, so that's what this example right here will look like. So we'll just put down that our restrictions on the side are x equals 3 and x equals -1. All right, so in the next example, we have f of x is equal to x plus 1 over x plus 2. And it's already been factored, so we can look and see if there's any common factors that we can simplify, and we don't see any. So we can just say that our restrictions are just to x equals -2. Since nothing cancels out and it doesn't behave like another different function, that means that well, you will most likely have a vertical asymptote at x equals -2. So let's go ahead and see if we end up getting a vertical asymptote there. So here's my graph, f of x equals x plus 1 over x plus 2. And we do end up getting a vertical asymptote at x equals -2. Okay, so again, our expectation of getting x equals -2 actually ends up happening. We do have a vertical asymptote there. Now, if you notice right here, however, our horizontal asymptote is not y equals 0. Our horizontal asymptote appears to approach y equals 1. So let's look at this right here and see if this is true. Yes, it does appear to approach y equals 1, which is really interesting. And we're going to talk about what happens and why we ended up getting y equals 1 and not y equals 0 in this example in just a minute. So right here, we can say that x equals -2 is our vertical asymptote. Y equals 1 is our horizontal asymptote. There still isn't a slant asymptote, and we don't have a hole, okay? So why did we end up getting y equals 0 for this horizontal asymptote and this horizontal asymptote, but we got y equals 1 for this one right here? Well, it has to do with the degrees that we have going on here. So in the numerator of this function, my degree is a 0 degree, but here it's a 1 degree. So my numerator has a smaller degree than my denominator does, which means that when I divide 3 by x plus 1, I can't really do it. I can't really divide x plus 1 into 3, so I get 0. Okay, here I have a larger degree in the denominator than I do in the numerator. So my numerator's degree is less than my denominator's degree. So I end up getting y equals 0 again. Now watch what happens when I try to do some long division with this. So right here, I'm going to go ahead and try to divide. So our function said f of x equals x plus 1 over x squared minus 2x minus 3, right? So I'm going to try to see how many times x squared minus 2x minus 3 can go into x plus 1. Well, how many times does x squared go into x? It doesn't. In order for me to be able to get this to work out for me, I need a negative exponent, which isn't possible. It's no longer a polynomial expression. So therefore, it goes in 0 times, which is why we ended up getting our y equals 0 right here. However, if I were to try to divide this x plus 1 by x plus 2, let's go ahead and see what happens when I do that. So when I had f of x equals x plus 1 over x plus 2 right here, I'm going to try to see, well, how many times does x plus 2 go into x plus 1? Well, x goes into x one time, and then when I multiply it through, it works for me. I have a negative denominator, or sorry, I have a negative remainder, but it doesn't really matter because we're talking about where it approaches for large values of infinity. This remainder right here doesn't make a difference when we get into large values of infinity. So that's why we end up getting y equals 1. So when I look at my graph here, I have my horizontal asymptote at y equals 1. Okay, so now for the next one, we have x squared plus 2x over x plus 1. So I'm going to go ahead and factor this one right here. So if it's f of x equals x squared plus 2x over x plus 1, when I look at my numerator, I see, oh, I have a GCF, so I'm going to factor out my GCF of x. So I've got x times x plus 2 over x plus 1. Nothing really is going to cancel out right here. So this isn't going to really do much of anything for me when I factor it. So let's go ahead and look at what our restrictions are. Well, we know x can't equal -1, and we also know it's not going to cancel, so therefore we can assume that we're going to have a vertical asymptote at -1 and that we won't have any holes at all. But let's go ahead and check and see if this is really true. Okay, so right here, let me close out of these. We've got in our numerator x squared plus 2x, and in our denominator we have x plus 1. So when I graph this out right here at x equals -1, do I end up getting a vertical asymptote? Absolutely. It tries to approach -1, but it just can't touch that -1. So that is correct. Now, if you notice, we also have a slant asymptote. It's clear it's approaching some slanted line, but what line is that? So let's see. It's clearly not approaching a horizontal asymptote, right? So let's try something. I'm going to say y equals x. When I graph that out, it doesn't appear to be quite right. So I'm going to just shift it up 1 and see what happens. Yeah, it definitely looks like it's trying to approach y equals x plus 1. So we know what our slant asymptote is going to be. So we know that there's no horizontal asymptote, but we do have a slant asymptote at x plus 1. Okay? Now the question is, how did I get that? Well, it comes down to my long division again. So let's go ahead and do our long division. I'm going to see how many times x plus 1 can go into x squared plus 2x. Well, x goes into x squared x times. X times x is x squared. X times 1 is x. When I subtract these, my x squareds cancel. 2x minus x is x. So then I figure out how many times does x go into x? Well, it goes in 1 time. So 1 times x is x. 1 times 1 is 1. Subtract it, I get a remainder of -1. But remember, that doesn't really matter when we're talking about large values of x. Like if you have a leftover -1, it's not really going to make a difference when we're talking about huge values, okay? So that's how we get x plus 1 as our slant asymptote right here, okay? All right, guys, 2 more. In our next example that we have here, we're looking at 9x over 1 plus x squared, and I want to go ahead and figure out what's going to happen here. So the first thing I'm going to do is try to see, well, can I factor it? So 9x over 1 plus x squared. This denominator is a sum of perfect squares, so there's no way that I can factor this. So this is as far out as I can go. So now, where do I have restrictions? Well, I would set x squared plus 1 equal to 0. So then I'd get x squared equals -1, which is impossible. So I don't have any vertical asymptote restrictions. So what I would guess is that I don't have any vertical asymptotes. That's my guess, and we'll see what happens when I actually graph it out. Now, for my horizontal asymptote, I want to see, remember, to figure this out, I just have to do my long division. So let's go ahead and do some long division right here. I'm going to see how many times 1 plus x squared will go into 9x. But instead of 1 plus x squared, we need to say x squared plus 1 right here. So how many times does x squared plus 1 go into 9x, or specifically x squared go into 9x? 0 times. So I would expect to have a horizontal asymptote at y equals 0. So now we discovered that we find our horizontal and our slant asymptotes the same way through long division. So since I get y equals 0 right here, I get a constant. I don't get a variable, therefore I don't have any slant asymptotes. And because nothing will simplify and it doesn't behave like another function, I don't expect to have any holes. So let's go ahead and graph it out and see what ends up happening. Let's see if we agree with everything that we have here. So we have 9x in our numerator and we have 1 plus x squared in our denominator right here. So it looks like we have the beginnings of a slant asymptote, but it doesn't continue, so we can't say that this has an actual slant asymptote. But we did figure out that we have a horizontal asymptote at y equals 0, and it's very clear just by our graph right here that we do have a horizontal asymptote at y equals 0, and that's the only asymptote that we end up getting, okay? All right, our last one right here is f of x equals 2x squared minus 3 all over x squared plus 1. So let's go ahead and do some factoring right here. So f of x equals 2x squared plus 3 all over x squared plus 1. Well, I can't factor my numerator because there's no GCF and there isn't any other type of factoring that I can do here. And I can't factor my denominator because it's just like the previous example. It's not a difference of perfect squares, it's a sum of perfect squares. So I'm going to try to find restrictions, but just like in our previous example, we don't have any restrictions, so therefore there is no vertical asymptote. Okay, now to find my horizontal or my slant asymptote, I'm going to have to do some long division. So let's go ahead and try to do some long division. So I'm going to figure out, well, how many times does x squared plus 1 go into 2x squared plus 3? Well, x squared goes into 2x squared 2 times. So 2 times x squared is 2x squared plus 2. When I subtract it, I get 1. So I've got 2 with a remainder of 1. Remember, this 1 is negligible when we talk about large values of x right here. Therefore, I should expect to have a horizontal asymptote at y equals 2. Since it's a constant, I don't have a slant asymptote. And since nothing's simplified, I don't have any holes. Okay, so let's go ahead and graph this one out and see what ends up happening. So right here, our numerator is going to be 2x squared plus 3, and our denominator is going to be x squared plus 1. So when I graph this out, this is what I end up getting. My asymptote is clearly not at 0. We figured out that it should be at 2, and if I look at my graph, it's very clear that it's going to be approaching 2. So everything that we figured out here, we were able to, first of all, discover through Desmos, and then we were able to verify once we figured out some patterns. So when will a function have a vertical asymptote? When there is a restriction in the denominator that hasn't been simplified out. Okay, so this will only happen when there is a restriction in the denominator that hasn't been simplified out. So for example, when I take a look at what I have here, we had a restriction in our denominator was x equals 1, but it was simplified out, so there was no vertical asymptote. Here we had a restriction in our denominator of -1, and it wasn't simplified out, therefore we had our vertical asymptote. Okay, so when will we have a horizontal asymptote? When there's two different possibilities. When the degree of the numerator is greater than, is less than or equal to the degree of the denominator. So let's take a look and see if that is going to work with the examples that we have here. So in this example over here, the degree of my numerator was less than the degree of my denominator, so I had a horizontal asymptote. Here, the degree of my numerator was equal to the degree of my denominator, so I have a horizontal asymptote. Essentially, it all comes down to your long division. If they have the same degree, or if the degree in the denominator is bigger, we get a constant. Therefore, it's going to have a horizontal asymptote. Okay, so now when will, we're going to skip question number 4 right now. When will a function have an oblique or a slant asymptote? Well, we had a slant asymptote in this example up here, and that occurred when the degree of our numerator was 1 more than the degree of our denominator. Okay, so we're going to say when the degree of the numerator is 1 more than the degree of the denominator. Okay, and again, it comes down to our long division. When we did our long division here, when we divide it out, if the degree of the numerator is 1 more than the degree of our denominator, we're going to get a quotient that is a linear factor. If we have a linear factor as our quotient, then we have a linear function as our asymptote, and linear functions we know are slanted lines. Okay, and then when will a function have a hole? Well, we ended up getting a hole only when we had, sorry about that, only when we had restrictions that we were able to cancel out. So right here we had a hole here, but that's because when we factored this numerator up here, it canceled out. One of our factors canceled out with our x minus 1 in the denominator. Same thing with this one right here. We had a hole because this x plus 1 cancels out with one of these factors in our denominator. So that is when we end up getting a hole. So we get a hole when the numerator and the denominator have a common factor. Okay, and when the numerator and denominator have a common factor of x minus a, then x equals a is a hole in our graph. Okay, all right, this is a lot of information to take in, but hopefully it made sense to you, and we'll do some practice with this next time I see you guys in class. Have a good day.